Here we look at the oxymercuration reaction for alkynes. The oxymercuration reaction for alkynes has some similarities with the oxymercuration of alkenes, but also ends up having a major difference. So we learned previously that an oxymercuration reaction for an alkene will lead to the most substituted alcohol. We add an OH group at the more substituted carbon and a hydrogen at the less substituted carbon. In an oxymercuration for alkynes, which generally uses water, sulfuric acid, and mercury sulfate, instead of forming an alcohol, we end up with a carbonyl. So as we'll see here, there are some similarities in the mechanisms as well as some pretty significant differences. The application of mercury to hydrate double and triple bonds likely dates back to the 1950s and Henbest, who published a number of these reactions. So let's look at the mechanism now. The mechanism here is relatively straightforward, and we won't really see a specific role for the mercury in this mechanism. But the alkyne, we do have a strong acid, gets protonated, giving us this unstable carbocation, which is immediately attacked by water. And then loses a proton to give us this alcohol. And so at this point, this makes it look like any hydration of an alkene. We've added a hydrogen on the less substituted carbon and a hydroxyl group on a more substituted carbon. Where this reaction changes is what we formed here is something we call an enol. Enol refers to the ene for alkene and the ol for the alcohol. And enols are something that we will study a lot more in organic too when we talk about reactions of carbonyl compounds. But what we're going to learn with enols right now is that under the right conditions, enols are generally unstable. And if you have either acid or base present, you have an equilibrium between the enol and its carbonyl. And in most cases, the carbonyl is more stable. And so very often that equilibrium will end up favoring the carbonyl. Now in the oxymercuration reaction of an alkyne, we do have a strong acid present. So what happens is the oxygen of the alcohol adds its lone pair in, which forms a carbon-oxygen double bond, and the pi electrons pick up a proton from the acid. And finally, that oxygen, which is positively charged, will lose that proton, and our enol in 2 steps converts to a carbonyl. And for most cases, you can't really stop this second half of the reaction, the enol converting into the carbonyl, from taking place. Again, under either acidic conditions or basic conditions, this is an equilibrium. And it's an equilibrium that, under most circumstances, very strongly favors the carbonyl. So oxymercuration, as it relates to alkynes, doesn't give us an alcohol, but it does give us a carbonyl. And carbonyls, as we'll learn in organic 2, are a very diverse functional group that are able to undergo a lot of different reactions. And so having a way that allows us to get from an alkyne directly to a carbonyl, when we start to study synthesis, will give us a lot of different possibilities. But notice in every case, the carbon that formed the carbonyl was the more substituted carbon. In this middle case, it didn't matter, and the reason it didn't matter is that alkyne is symmetric.